Yeah, welcome everyone to this seminar. That's part of the seminar series we run under the Geophysical Flows Lab Center of Excellence. We record all these seminars and put them up on a YouTube channel. So please feel free to view the channel and look at various seminars on various topics that we have done so far. So today it's a pleasure to invite Dr. Javier González-Rocha, who is recently started as an assistant professor in the Department of Applied Mathematics at the University of California, Santa Cruz. And he is currently visiting IIT Madras and being hosted by Professor Devaprakash Muniraj in the Department of Aerospace Engineering. So, may I request Professor Deva to just introduce Javier and we get started with the seminar.
Yeah, sure. Thanks, Maya. Hello, everyone. So it's my pleasure to welcome Dr. Javier González-Rocha. As was mentioned earlier, Javier did his PhD in aerospace engineering from Virginia Tech, and where he worked on using unmanned aircraft systems for primarily sensing in the lower atmosphere. And he was involved in many campaigns where he collaborated with other atmospheric scientists and oceanographers. So after his PhD, he moved to University of California, Riverside for his postdoc, where he did dispersion modeling, and he used unmanned aircraft systems to measure temperature and other measurements in the lower atmosphere. And very recently, he started his assistant professorship in University of California, Santa Cruz, in the Department of Applied Mathematics. Right? And please welcome Javier. I think with that, I'll hand it over to Javier. Javier, you can carry it.
Yeah, thank you for the invitation. I'm really Deba mentioned this work began at Virginia Tech as part of my PhD. I hope you'll enjoy it. So the title of the presentation is Developing Aerial Robotic Systems for On-Demand Wind Sensing in the Lower Atmosphere. So the big question is, why is it important or critical to measure wind in the lower atmosphere? And especially measuring it in real time. And so here are just some examples. There are plenty more, but here are some of them. So starting from the left, so here is if you want to respond to environmental flow hazards, you want to know what the wind is doing. So in this case here, we have natural gas spilling into the atmosphere in the Los Angeles area. And this is on record the largest leak, right? So if you are trying to remove people from harm's way, it's very important to understand what the wind fields are. Another application is precision agriculture. So if we want to be efficient in how we spray both fertilizers and pesticides, we need to understand when the atmospheric conditions are right. If we spray when it's too windy, for example, the pesticides are going to fly, and so you're fly away or drift. And so you're going to lose efficiency and then potentially impact downwind communities. And then to the right, far right, really, if we measure wind with other parameters such as temperature, pressure, and relative humidity, we can do things like improve weather forecasting models that allows us to respond to extreme weather events, which we're all having to deal with more and more, whether you're here in India or you're in California. So let me then step on to sort of kind of give an overview of wind sensing technologies, right? And so when I think about wind sensing technologies, there's two types of wind sensing technologies. There's in situ sensors and there's remote sensors. And so here, the list that I'm not showing, that I'm showing, excuse me, is not comprehensive, but it's to sort of kind of paint the picture. So on the left, you have in situ sensors, and so these sensors collect um, point measurements with high resolution, right, depending on the sensor. And so these sensors can cost anywhere from 400 to 10,000, maybe even more. So if you're using like a 3D sonic anemometer, Campbell Scientific, that's more on the order of 15,000. So there's a trade-off, right? So you get very high resolution temporally, but if you want to understand how winds are changing with height or across a surface, you need to buy more of these sensors. And so you also need to have access to the land so that you can set them up. And then to the right, we have a SODAR and a LiDAR. So a SODAR is essentially, let's see if you can see my marker, hopefully. So a SODAR is just an array of speakers, and these speakers will chirp an acoustic signal into the atmosphere. And then it'll listen to the return signal, and using the Doppler effect, it'll triangulate the wind velocity. So this sensor will cost anywhere from 41,000 to 170,000. And then to the right of that is the LiDAR. So it's works on the similar principle, but instead of an acoustic signal, what it's using it's light. And so those sensors can be more on the order of 200,000 K. And so my research, placing this in context, has been focused on exploring how we can use aerial robotic systems or uncrewed aerial systems to augment or complement existing technologies. Now, why explore this technology? This technology is highly mobile, economic, easy to operate, and it's actually very portable, which makes it easy for on-demand measurements. Now, with regards to wind sensing using robots, I was not the first person to think about this concept. There were already quite a few people in this space trying to understand how we can use aerial robotic systems to sample the atmosphere. And so the first approach, which I'm showing to the left, is just essentially using the aircraft itself as a platform, right, as a dedicated carrier for the atmospheric sensors. So what you see here at the top, that's the sonic anemometer. Now there's some drawbacks with this approach. So one of them is that you have to bear the payload of the sensor, you have to power the sensor, and then you have to also account for the motion of the aircraft as the aircraft is flying. And you also need to account for the wind field corruption that the propellers might be contributing to. Now on the right side, so this phase, so this is more has explored, can we use the aircraft itself as a sensor? And so Newman and Matias were actually, the paper by them was the first one that explored this approach. Is essentially, they conducted wind tunnel experiments, and they essentially mapped the tilt of the aircraft, looking at the roll and the pitch, how that changed at different wind conditions. Now, one of the drawbacks with this approach is that it assumes that the wind is constant. So to relax this assumption, I've actually this is where a lot of my PhD work focus was on developing dynamic models to estimate a time-varying wind velocity and comparing these estimates to the baseline, which is the kinematic model, to see if we can get higher fidelity or higher accuracy wind measurements. And so developed the three models. So there are really two. I mean, the kinematic model was already existing, but just to kind of give you an example. So In the kinematic particle model, so we assume that the aircraft is just a kinematic particle. It doesn't even have mass, right? And so we assume that the inertial velocity of the aircraft is the sum of the wind velocity and the aircraft's relative velocity. And the air relative velocity we consider to be an input, and the wind is an input disturbance. You know, and for a fully actuated aircraft that can quickly respond to wind disturbances when it's hovering, then the wind estimate just becomes the negative of the air relative velocity. However, like I mentioned, the limitations of this model is that it doesn't account for the dynamics of the aircraft because the aircraft actually has mass. It responds dynamically to wind disturbances. And so therefore it might have some limitations in accurately measuring winds. The next model, the dynamic particle model. So we have here, so where the inertial velocity is the sum of the wind and the air relative velocity. And then in the dynamics, we have the effect of the wind contributing as an aerodynamic force. So here in this model, we are now considering forces, right? Masses and forces. And then in the more complex model, the rigid body, or maybe I should say sophisticated model, we're accounting both for translational and rotational dynamics, right? Both in the kinematics and in the dynamics. And when I started evaluating these models or considering these models for estimating wind velocity, I was interested in using them for the hovering condition. The dynamic particle and the rigid body are highly nonlinear. So I linearized the dynamics about the hovering condition. And so we obtained a model in this general form, which is the time derivative of the state vector is equal to the unforced dynamics, the control dynamics or the input, and then here gamma W is the wind disturbance. And so the question really that I posed was, considering the vehicle was a sensor with low pass characteristics, does the bandwidth of the wind estimate increase with the fidelity of the model? I mean, do we get a more accurate wind estimate with a more sophisticated model? So great. So now that I've set this frame, so let me tell you what's involved in characterizing each one of these models. And so I'll start first with the kinematic particle model. So to characterize a kinematic particle model, you can either do a wind tunnel experiment, like the ones that I mentioned, or in the absence of a wind tunnel, what I did was I went out on a day where the winds were relatively calm, and I flew transects from point A to point B. Point A and point B were about 100 meters apart. And so I varied the aircraft's velocity. So I went from 3.9, almost 4 meters per second, all the way up to 7.3 meters per second. And I varied the side slip angle. So the side slip angle is shown here. So this is the side slip angle is essentially the angle of the air relative velocity to the front of the aircraft. And so then using the roll angle and the pitch angle, we characterize what I call a side flow angle or a tilt angle. We can call it that, right? So it's essentially how much is the aircraft tilting. And so I guess until I jump into the results, just to give you, so here's the picture of the aircraft. So really essentially, alpha, the side slip angle, is the angle between B3 and I3, right? Where I3 is pointing downwards. So it's an inertial reference frame. And B3 is the body reference frame. So we get this plot. So it's essentially one of the interesting things that we found was that it's quite linear for the range that we tested. And also we noticed that that any effect that might be caused by the change in the side slip angle is actually within the noise of the measurements. And this could either be because we were using a relative low cost aircraft, or it could just be that essentially because it's quadcopter is fairly symmetrical, it's really not that relevant. So using the simple model, then, if we can compute from roll and pitch what our side flow angle is, then when we can obtain a relative velocity, right? So it's essentially we've generated a lookup table. And so again, to do that, we did a total of 16 experiments. All right, so now to characterize the dynamic particle model, this one was a little bit more involved. So now we need to understand how forces are generated. And so to do that, I did wind tunnel experiments at Virginia Tech. And so the wind tunnel wasn't big enough. So what I did was I characterized how much thrust a single thruster generated. And so here's the thruster mounted on a sting balance. And so a sting balance is essentially an instrument that measures forces and moments as the aircraft, not the aircraft, but as the propeller is spinning under different conditions. So the just to give you an idea of the parameters that were varied, we varied the air relative speed, with it's obvious. So we started with a control case where there was no wind, and then we went from a flow 11 meter per second flow up to a 16.4 meter per second flow. And then we varied the propeller speeds, and so we went from 4,000 RPM to 5,000 RPM in intervals of 500 RPM. And then we varied the side flow angles, since again, this is the tilt. And so we went from 0 degrees all the way to 90. And in this picture, just so that people can make sense of it, so alpha is defined as the propeller axis, the angle between the propeller axis and then this axis, which is coming right along the sting balance. And so the things that we measured were the PWM and then the 3-axis forces and moments. Using these measurements, then we compute the advance ratio and the thrust coefficient. So the advance ratio is essentially just the air relative velocity coming, along the propeller spin axis, normalized by the N is the RPM, and D is the diameter of the propeller. And then the thrust coefficient is the force normalized by the propeller's tip velocity squared and density. So here are the results, right? And so the idea is from these experiments, we want to generate some sort of model that can relate, that can tell us how much force is being generated at different conditions. So the first observation when we look at the RPMs here in this 3D plot is that the measurements are actually quite collapsed. So that suggests that within the variation that we tested, that there isn't a large change. Furthermore, when we collapse these measurements, and we just, we look at this plane view and we just look at how the thrust coefficient is changing versus advance ratio, we actually see that for most of the range, it's a linear relationship, which was actually quite surprising as well. So this means that we can use this model to understand how much thrust is being generated. And it's a linear model, at least for this aircraft. One of the things I guess that I didn't mention that I just want to highlight, it's 156 experiments, right? So to characterize the second model is just tremendous increase in effort to generate that model. Now, the third model, which we call the rigid body model, is for this we use system identification. And so essentially, system identification is essentially data-driven parameter estimation, right? And so in this case, we just fly the aircraft. We're interested in characterizing its dynamics under hover. So we just have it hover and then we excite it, right? And so we provide it with sinusoidal inputs. In this approach, we decompose the dynamics of the aircraft into a plunge mode, yaw mode, roll mode, and pitch mode, right? Once we have the input and the output measurements, we first determine the model structure of each of the plunge, yaw, roll, and pitch models. And we do this essentially using what's called stepwise regression. So once we get a good model structure, then we feed that model structure into an output error parameter estimation scheme. And so here shown below, in which essentially we're just minimizing. It's a cost function that's minimizing the error between the measurement and the model. And just to sort of illustrate the whole process on the left, so we do the flight testing, we do the input-output measurements, we do the model determination. If we have a good, a well-posed model, then we go on to compute parameters using output error parameter estimation. Then once we do the parameter estimation, then we do the validation. And so for this, we did additional experiments. And so here I'm just going to show you the results for the roll mode and the pitch mode. So essentially, starting with the roll mode, the aircraft was in hover, and then it was just excited. So you can see the translational velocity, the roll angle, the roll rate, and this was the input that we provided it. And so you can see the black is the simulated, and then the dash is the experimental, and the match between the two suggests that the model that we learn is a really good model for the aircraft. Here's the pitch model. Similar results. So we have the translational velocity, the pitch angle, and then the pitch rate, and then the excitation. And you can see that for the most part, it did really good. And so this was a very interesting finding that we can actually use the system identification to characterize these models, because it only took us 8 flights, right? So to characterize the simplest model, it was 16. The second one was 154, if I remember correctly, and then for this it was 8. Okay, so now we have the models. How do we estimate wind, right? So if we're using a kinematic particle model, again, the wind is just the difference between the inertial velocity of the aircraft and the air relative velocity. And the air relative velocity we can just obtain by computing or essentially determining the side flow angle. But using the latter models, or the dynamic particle model and the rigid dynamic model, we actually synthesize a state observer. And so to synthesize a state observer, we first formulate what's called a wind augmented model. So a wind augmented model is basically a model where the state vector of the aircraft, which is X, Y, and Z, right, which tells us position, then the 3 angles, which tells us attitudes, and then the Euler angles, and then the time derivatives. So that makes the state vector, and then wind velocity is the additional 3 states that we augment, right? So we write it in this form, x subscript a, and so here we see, and so here we've now, the wind disturbance, we've now considered it to be part of the dynamics in some sense. We assume, or we don't assume, but we know that we can measure the state vectors of the aircraft. This is the position, attitude, and time derivatives. And then we do what's called an observability analysis. And so if the system is observable, in theory, we should be able to estimate the states, the wind velocity states, right? And so we can you do that just using a state observer of this form. Okay, so after I formulated the state observer, now there's the question of.
Sorry, have you a quick question? So what's special about rank 15, or is that just an example there?
Yeah, so when we look at the dynamic, so when we look at the system here, this is a 15 by 15, right? So if the rank is 15, it means that the system is observable. What does this mean? This means that we can use the states that we're measuring to estimate the states that we're not measuring. So in this case, the wind we're not measuring, we're inferring it, right?
Yeah.
So this is telling us that our GPS information and our IMU information can be used to estimate wind, which is the thing that we're not measuring.
I see. Okay, thanks.
Does that make sense?
Yeah, thanks. Yeah.
All right, and so So here, so the next step was just to look at the bandwidth of the dynamic models, and in comparison to the bandwidth of conventional technologies. So at the bottom, I have three different sensing solutions. So this is a SODAR, and it's sampling 12 times per hour. Then we have a LiDAR, 12 times per hour, and then we have a SODAR that's working a bit faster, twice as fast, 120 cycles per hour. And so when we put them in this map, which is sort of a general representation of the turbulence in the atmosphere, we see that only the sensor that's sampling 120 cycles per hour is actually capturing the turbulence that's happening on the 1 minute scale. So when we look at the aircraft, so we compute the observer bandwidth for both the dynamic and the rigid body model, and so we plot them. And so this tells us that in theory, the drone, at least the one that we were using, can help us capture those fluctuations. So this is a great result, but then now let's take the theory to practice. So here are, I hope you can see this. So this is the video. The video's playing. Is it playing on your end?
Yes.
Yes,
So
we
these
can.
are
Yes.
so these are experiments that I conducted. So the aircraft is essentially just hovering right at the same next to this weather tower. So this weather tower has a sonic anemometer and a wind vane, and so you can see how the aircraft is essentially responding. And so here are the results.
Just a quick question. Is there an
Yeah.
issue that you're in the sort of in the wake of the tower, no? I don't know, I mean,
Yeah. Yeah, potentially. And I think I think you're totally right. I mean, but it might also, based on the comparison, it might see that the actual wake effect might not be significant, you know, but I think that's a really good point.
Yeah, sure.
So here are two plots. So the first one I'm showing wind speed versus time. And so the black signal is the signal from the sonic anemometer. The green signal is from the kinematic particle. The blue is from the dynamic particle. And then the red is from the rigid body. And so in this case, the winds were fluctuating between 2 meters and 3 meters per second. And you can see the red, which is the rigid body model, outperform the other ones, right? So at the bottom, I'm showing the root mean square error. And so you can see as the fidelity of the model increases, so does the fidelity of the wind estimate. So that was very interesting finding. And that held consistent for various wind conditions, at least within the range that we were operating. So as you can see to the right, during this period, the winds went from about 2 meters per second to 5 meters per second. And again, you see that the rigid body model did better estimating wind velocity. So great. But now, what about if we're trying to understand how wind is changing in the planetary boundary layer? Hovering at fixed heights is not efficient, considering that we have limited battery power. So the question is, can we profile wind velocity while flying vertically, right? While ascending at different steady rates. And so I explore the extension of the rigid body model to profile wind velocity. And so I used a linear parameter varying schematic, or more scheduling, really, like this concept of control scheduling, but it's really not doing control scheduling. What we're doing is the scheduling of parameters, right? So we're scheduling A and B based on the ascent velocity of the aircraft. And so we are considering a number of velocities that range from 0 meters per second to 2 meters per second. And so we have a model for each one of those ascent rates. And so in this approach, we essentially did system identification again for each one of these conditions. And as you can see in the video, we're ascending at a fixed ascent rate. Then we excite the aircraft. Then we come back to a steady state. We learn the dynamics. We validate the dynamics, and then we synthesize an observer. And then we do validations. So after characterizing the different models, I conducted field experiments again, and so to benchmark this framework against the conventional remote sensing technology. So we had a sonic anemometer, a low range SODAR, so which can measure from 30 meters, long range, excuse me, that can go from 30 meters to 400 meters, and then we have a short range SODAR, which goes from 10 meters to 200 meters, and of course the aircraft. And so, just to get an idea, the SODARs were about 60 meters apart. The sonic anemometer was right in between, and then the aircraft was off to the side. So this is just a quick video of the experiments that were performed at Virginia Tech, and so this is sort of the measurement that we're able to get. So here are the results. So to make this comparison, I essentially looked at the wind velocity measurements at 110 meters above ground level, right? And so looked at the measurements that were being reported by the long range SODAR and the short range SODAR. And so so here the green triangle is the long range SODAR, and then the red rectangle is the short range SODAR, as you can see. And then this, yeah, and then the markers below are essentially the estimates from the aircraft ascending at different rates, right? So this is the estimate at 0.5 meters per second. This is the estimate at 1 meter per second. And this is the estimate at 2 meters per second. And so this top panel, we're looking at wind speed over time. And at the bottom, it's wind direction versus time. And you can see that the drone measurements actually fall within the trends of the two remote sensors. We wanted to do a more rigorous validation of this, but one of the things that we discovered actually from this experiment was that when you fly a drone too close to a SODAR, you're going to corrupt the wind measurement from the SODAR. So this is why we're just looking at the measurements before and after to make this assessment. But overall, you know, the results show that this is very promising for measuring wind velocity, considering the disparities in the scales of the measurements. All right, so more recently I've explored, can we get the same wind sensing performance from every aircraft configuration? And so I've explored wind sensing with puller and pusher hexacopters. They're here on the left. They may look like they're the same aircraft, but there is a subtle change. So the puller aircraft has the propeller at the top, and the pusher aircraft has the propeller at the bottom. And actually, collaborators at the University of Michigan discovered that there were big distinctions in the lift to drag ratio of these two aircraft. So the pusher hexacopter actually had a lower lift to drag ratio, which means that it's less efficient for forward flight. Now, I posed the question, or one of the things that I got curious about was this thing that is perceived as a weakness, can it actually be a strength for inferring wind velocity? So we did experiments. This video you've already seen. So we've characterized the rigid body dynamics of the two aircraft. And that's just on the video on the left. And on the video on the right, this is the aircraft just sustaining hover in between an array of sonic anemometers. And so here are the results on the wind estimates. So on the left, focusing first there's wind speed and wind direction versus time. The yellow is the sonic anemometer, and and then the blue or the square is the drone, or is the UAS. And so you can see wind speed. It's very well captures the sort of peak or the change in wind speed, as well as wind direction. Pusher hexacopter as well. Great performance. So for measuring general trends, they both appear to be doing a good job. But to really get at the question of like, is one better than the other at measuring wind velocity fluctuations? We did experiments or an analysis where we actually looked at the power spectrum of the wind velocity fluctuations, right? And so we compare both the estimate from the aircraft and the sonic anemometer. And so here are the results. So you can see that the aircraft can capture, here the puller can capture the trend in turbulence, but still there are quite some big errors. And when we look at the pusher aircraft, aircraft actually does a bit better capturing the trend. And so one of the interesting findings is that the configuration, excuse me, actually does matter. So if we are interested in measuring in wind velocity fluctuations, pusher hexacopter might render us better wind estimates. And so now that I talked about sort of wind sensing, I want to just take a leap into sort of an application of sort of kind of connect dots as to why wind sensing is important. So here, this was the recent project that I was part of. This was the ALPHA project, the Advanced Ranging Predictions for Hazards Assessment. And so this was led by MIT. And so we was at Virginia Tech. So we were one of the many participants. And so one of the things that we wanted to explore was if wind estimates can actually help us improve search and rescue. Why? Search and rescue is a global problem. In 2016, the UN Migration Agency recovered over 5,000 deaths among people trying to reach Europe by crossing the Mediterranean Sea. So that's just a lot of death just in one region. Putting in the context of the U.S., in the U.S., the Coast Guard responds to about 4,000 search and rescue events per year. They only have about 75% success. And the reason why is because there's a lot of uncertainty as to when and where the victims enter the water. And so, and then on top of that, they have the constraint of that they need to respond within 6 hours to find the person alive. Right now, there are models used to make probability maps, but those, so these are based on wind field conditions and also what are called leeway parameters. But some of these leeway parameters are very uncertain. And then based on that, searching patterns are determined and methods are deployed. So so basically in this application, we're exploring, can the measurements from the drone be used to get leeway measurements or estimate leeway measurements much quicker. And so a leeway measurement is just the motion of an object induced by wind, typically considered at 10 meters above sea level, in waves relative to the ambient current. And so the ambient current in the ocean is anywhere between 0.3 and 1 meter. 1 meter. And so these are the leeway parameters essentially. So there's two. There's the downwind leeway factor. So and then there's the crosswind leeway. And so I guess before I advance, I'll say a little bit more about this. So the way that these parameters get characterized is, so in the case of let's say for a boat, so engineers and scientists will integrate a boat with a sonic anemometer to measure the wind conditions. And then they'll also have some other sensor to measure the currents. But this is very involved. So the goal is, can we use a drone instead? Because a drone is easy to deploy. So we did experiments first in a lake where we threw in a mannequin, and so a mannequin is just a surrogate of a human next to a drifter. Here's a picture. We integrated both the mannequin and the drifter with a GPS tracker that's giving us high resolution information. So here's the drifter, here's the mannequin, and we're looking at the relative displacement. So the differential movement due to windage, essentially. In the ocean, we did very similar things. So here's the ocean mannequin, and then the Code Davis drifter, which many of you might be familiar. Deploy that into the ocean both at the same time, then use the drone to measure wind velocity over the mannequin, and collect other position measurements based on these Pixoc GPS modules, and then we computed the leeway. So just to kind of give you a highlight of the field experiment, it's a short little video. So we're obviously out in the ocean, we're dropping these mannequins in. Again, the drifter and the mannequin are released at the same time. And we release the drone, using the drone to estimate wind velocity, and then we're tacking on a low pressure, relative humidity, and other parameters. So here are the results. One of the things, this is very preliminary, but to us it was interesting that a significant number of multi-rotor assisted leeway corrections were found to be in close agreement with values published by Breivik et al. In 2011, where Breivik used conventional methods. So the significance of this is that we can essentially use drones to characterize the leeway for different things, not only humans, but you can think about small parts that are of interest, that are drifting in the ocean, things like trash, things like in the case of a wreckage, we understand how things are drifting. Drones might be a great solution to help us characterize these leeway values. And so just sort of to kind of close things up and kind of give you a bigger picture of where the things, that I'm working on. So I'm very interested in dynamics control and estimation, aero robotic systems, and atmospheric ocean transport. And so I'm really happy to be part of this group and to sort of kind of build synergy and discuss ideas. But really all of this is just like, hope it highlights the potential for uncrewed aircraft systems for real-time atmospheric observations and prediction tools. And so with that, I'll just, some acknowledgements. Dr. Shane Ross from Virginia Tech, Dr. Irina Ripina from Hui, Dr. Craig Woolsey from Virginia Tech, Dr. David Schmalley from Virginia Tech, Dr. Thomas Peacock from MIT, and Dr. Stefan DeWecker from University of Virginia, and NSF and NASA for sponsoring this research. So with that, I'll just open it for questions.
Yeah, thank you, Javier, for the wonderful talk. Audience, if there are any questions, you can show hand. Yes, Sudarshan, please go ahead.
Hi, Javier. Thanks for the talk. It was a really nice talk. I am actually a part of a photonic sensors community that's trying to make sense out of UAVs and applicability of my sensors that I'm developing in this context and realm. So I saw you baselining most of your measurements with SODARs, right? These are acoustic-based anemometers. I just wanted to hear out from you, like, what are the standards? Are SODARs the standards for wind velocity, or are there some that are based off of optics or lasers to measure
Yeah,
wind velocity?
I would say LiDAR is the standard, or at least I've seen more people doing comparisons using LiDAR.
Okay, so what's the advantage that LiDAR brings?
It in some cases it has a higher, has a faster response.
Okay, I
Yeah,
see.
and then the other thing is, LiDAR, you can go much higher into the atmosphere, and so you can go kilometers. You can profile a couple of kilometers up. With SODAR, 400 is the highest I've seen.
I see. Okay, and how heavy is this SODARs usually?
And you definitely need two people to carry it. So
Okay,
I would say, depending, I would say about 60 kilograms is perhaps the lightest.
all right. Thank you, Javier.
Thank
Nice
you.
talk.
Yeah. Oh, there's someone.
Yeah,
Please.
that's me.
Yeah.
Um, Hey, Javier, that was a really nice talk. Thank you so much.
Yeah.
I had one question. You were showing towards the second half of your presentation, you were flying the drones over the oceans, etc. Just curious, is that how do you just sort of you pilot it manually based on what you're seeing at that point, or do you have pre-planned missions that you plan to execute beforehand?
Yeah, our research vessel was quite small. So as you saw, really someone had to catch it, right?
Right.
So it was all manual.
Okay. And you had, did you have multiple cameras on board? Or like I saw that you were panning the video. Was there maybe a camera on a gimbal and you had a secondary camera
Yeah,
setup? Or?
there was a camera on the aircraft, and then those of us that were, like, I had a camera on my helmet. So we had, just for the purpose of recording, we had cameras on different points. But yeah, I mean, the for the purpose of science, we only had one, uh the gimbal from on the drone.
Okay, understood. Yeah, thank you so much.
Yeah.
Anyone else?
Maybe I can ask a question. Am I audible?
Yes.
Yes, yes.
So it was very interesting to see that the puller versus the pusher dynamics in the system identification of your wind speed. What do you think is the dynamics which is playing in a role in this measurement per se?
Oh, that's a really good question. So essentially, what's happening, my conjecture is this: we have to measure it to really say that this is what's going on. But my conjecture is that for the pusher hexacopter, the flow has to go around the arm before it goes through the prop. So the prop is actually seeing more turbulent flow, and so because the prop is seeing more turbulent flow, it generates more drag.
Okay, I see the point.
Does that make sense? Yeah.
Okay, so that's the reason why you presume that, but okay, it generates more drag. I understand that aspect, but why do you think the estimate is better from the pusher rather than the puller?
Oh, yeah. So because it has more drag, it's more sensitive to changes in wind.
Okay, so the state
Yeah.
estimator is able to perform better.
Right. Because drag is a function of air relative velocity of the wind.
Or the square of the velocity.
Yeah.
Okay, that makes sense. Thank you.
Yeah. Great question.
Any other questions?
Yeah, sorry, Deva, I had to.
Okay. No worries. You have a question, Emma?
Yeah, I was just. I mean, I stepped out. I guess the meeting is over, and you guys are having a private conversation.
No, so we are just having a Q&A if with Javier.
Okay. Yeah.
I mean, if you have any questions for him.
Yeah. Let
Feel
me
free.
just gather my thought. As I said, I had to step out for a few minutes. So I'll
Okay,
just
okay.
yeah.
No worries.
Just give me a
No
minute.
worries. Yeah. No worries. Yeah. So in the meantime, Javier,
Yes.
so I want to ask you, so have you tried online estimation of wind or any of these parameters? So most of the work has been offline, right? So you collect
Yeah.
data and then, so have you tried in any of your problems to estimate these, especially wind online?
I have not, but that's the next frontier. I
Okay.
think especially with this concept of sensor mobility, which
I think I lost you for a moment.
I was
Yeah.
just talking about in the context of advanced air mobility, right? This idea
Okay.
with flying through urban canyons.
Okay.
Um, I think the idea of real-time wind sensing is very important.
Mm.
Yeah. So I haven't done it, but it's the next step. You know, it's a critical
Okay.
urgency.
But your algorithm can be directly implemented, right? That I
Yes.
mean,
Yes.
there's no major change that is required.
Yes, that is correct.
Okay. And like, what is the sort of winds that you can estimate with reasonable accuracy?
About 5 meters per second is what I've been able to validate.
Okay. It has to be at least 5 meters per second for you to
Yeah.
estimate it
Yeah.
accurately. Okay. And what's the sort of accuracy levels you have achieved so far? I mean,
Yeah. So that you start losing accuracy in your wind speed estimate, but the wind direction actually is still at higher speeds. Um, so that might be resolved by characterizing a model, right? Because the model assumes that the wind is just a disturbance, right? And so the winds are much higher than essentially the model doesn't account for that. So I for sure you're gonna get an increase in air.
okay.
Yeah.
Okay. Yeah. Makes sense. Makes sense.
So, Avi, just a related question.
Yes.
If the wind has fluctuations, what time scales in those fluctuations you surely cannot capture with this model? What would be the physical considerations setting limits on these time scales?
Yeah. So the physical limitation is the dynamic response of the system, right? So if you have a heavy drone is going to respond slower. But if you have a small drone, the drone actually will respond quite fast, right? So um, I don't have an exact number to give you, like in in the scale, but it's in the scale of seconds, right? So um, I'll show it in another presentation. I've actually there's been some flights where the drones have actually captured some flows, some changes in flows that are relatively fast, and so we're flying next to a sonic anemometer, and so the sonic anemometer is a good validation because it's sampling at 20 hertz. So, but yeah, I think in the changes that are in the scale of seconds, I think the aircraft can recover.
Thank you.
Okay. Any other questions for Javier?
Maybe I can ask one more if there is time. So,
Yeah, sure, Abhilash, go ahead.
yeah. So Javier, I can kind of see that you're trying to look at the wind speed. I just want to kind of invert the problem and ask you the question. Let's say that some of the dynamics of my aircraft are not known, of the drone are not known, and I would like to estimate them. And let's say for a fact that the wind is not the consideration. Would the same approach be a good approach to do system identification of the parameters of the drone?
Yes.
And yeah, please go ahead.
No, I was going to say, in fact, maybe one of the things that I didn't mention, the system identification, when we do it, winds are very common. In fact, it'd be ideal if there's no wind, right? Because we're really trying to get at what are the real dynamics of the aircraft. Because if we can characterize that, then we can better understand what are the deviations that the wind disturbance is contributing to. So whether the wind is there or not, or I guess what I'm trying to say, whether the context is wind sensing or not, I think system identification is a good approach to learn the dynamics of the system.
But in my experience, generally the problem comes when the wind is there and I still don't know the dynamic model. Usually it's the challenge is there. How much of the contribution is coming due to the wind and how much would be actually the drone's uncertainty, which I don't know about.
Right.
Any good approaches to solve that issue?
The only way to solve that issue would be to characterize the dynamics of the system indoors.
Sorry, I missed that last part. The system?
Indoors, when there isn't the effect of the wind.
Okay. All right.
So using the motion capture, using a motion capture system.
Okay. I see the point. Usually I work with autonomous surface vehicles, so I was thinking in that context, and when we take the vehicles to the lake, the chicken and the egg problem really crops up there, with whether the dynamics is really due to the wind or is it due to the fact that my hull form is exhibiting some interesting dynamics. So
I see. Yeah.
Thank you, though. I probably will catch up with you sometime.
Yes, please do. I really hope that you all found this conversation, this presentation, and chatting with you all soon.
Sure, I will probably get in touch with Arjun and get in touch with you probably through there.
Great.
Okay, if there are no more questions, then I once again thank Javier for this talk. It is a pleasure hearing from you.
Thank you.
And, thank you.
All right. Goodbye, everyone.
Yeah.
Thank you.